In this video, we quickly derive the formulas for equivalent resistance for series and parallel combinations. We make a quick note on the comparison between the equivalent resistance and each of the individual resistors in the combination, and then we finish each type with a simple example. So if I check out our series combination real quick, I'm going to mark two nodes on this just to emphasize that what we're doing here is saying if we clip out R1 and R2 out of this circuit, and then replace it with REQ, we should get exactly the same behavior. In other words, the same total current through the circuit. That's what we mean by an equivalent resistance. So for one thing, I know that the total current in the circuit is going to be the same when I make this replacement. Second, I can see that the total voltage drop across the series combination R1 and R2 is V. It's the same as the voltage drop across the equivalent resistor. But that voltage drop across R1 and R2 can be split into two voltage drops, one for each of the individual resistors. And those two voltage drops better add up to V, and that's where we begin the derivation. So I'm going to apply Ohm's law to each of these resistors, V equals IR. And on the left hand, I have the equivalent resistance, so I have I times REQ. On the right hand side, I have the same I, again the same total current flows either way we do this circuit, times R1 plus I times R2. And because those I's are the same in both circuits, they cancel out, and I immediately obtain my formula for the equivalent resistance of two resistors wired in series. Now just a quick note on comparisons here, because these are important sometimes for conceptualizing what a circuit is going to do. I can tell immediately that the equivalent resistance is bigger than either one of the participant resistors. And then our quick example. I want to get the equivalent resistance of this simple series circuit. I have a 5-volt battery, two resistors, 220 and 100 ohms respectively. And so REQ is so simple that I don't really need to show any of the math here. You just add them, and I get 320 ohms. So now I'm visualizing the circuit in this simplified form. It's just the battery and the equivalent resistor, and I can find the current by saying I equals V over R. So I'm just turning around Ohm's law, and V is 5 volts, and R equivalent was 320 ohms. I shifted the decimal place on this answer to get 15.6 milliamps. All right, now let's check out our parallel combination. The thing that's the same for each resistor now is the potential difference across it. I can see the high side of R1 is connected to the positive terminal of the battery, the low side to the negative terminal, and that's a voltage of V. It's also going to be a voltage of V over R2 and over the equivalent resistor that I replaced them with. In that equivalent circuit, I'll go ahead and show the total current. And that same total current flows in this branch of our original circuit, but it gets split into two pieces when I hit that node. Now, since charge is not allowed to build up anywhere, I know that I is equal to I1 plus I2, and that's where we start the derivation. Then I use Ohm's law, and I can say I equals V over R over each of these resistors. So looking at the equivalent resistance, I have I equals V over REQ. Again, that V is the same thing for all three of these resistors. I1 is going to be V over R1, and I2 is going to be V over R2. The V's are the same for all three, and those cancel, and I immediately arrive at my formula for the equivalent resistance of a parallel combination. So far, our equivalent resistance formulas are easily extended to 3 or more resistors. I just keep adding on terms that look like this. For series resistors, I would just go R1 plus R2 plus R3 and so on. For parallel resistors, 1 over the equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 and so on. But there's some advantage in reworking the parallel formula to actually solve for R equivalent in general, because it allows us to compare the equivalent resistance to the resistance of the individual resistors. So what I'm going to do to solve for REQ is take the reciprocal of both sides of the equation. Then to get rid of the complex fraction, we multiply the top and bottom by the least common denominator, R1, R2. And I end up with an R1, R2 in the numerator. And when I distribute R1, R2 to 1 over R1, the R1's cancel and I just get R2. When I distribute it to the second term, the R2's cancel, and I get R1. So this is a popular reworking of the parallel equivalent resistance formula. I'm going to put it in order and call it R1 plus R2. And now I'm going to find my comparisons with the original resistors. And the idea is this. I can say that Req is definitely less than R1, R2 over R1. Because R1, R2 over R1 has a smaller denominator than R1, R2 over R1 plus R2. So I just removed R2 from it, made the denominator smaller. It must be a larger quantity. So now it's bigger than Req. And I just showed that Req is less than R2 itself. Repeat this sort of idea, removing R1 instead of R2. And I find that R equivalent is less than R1. So the parallel equivalent resistance is less than the resistance of each of the resistors that are in the combination. And we'll see that in action in the example. My parallel equivalent resistance should be less than 100 ohms, less than either one of these. So I'm going to go back to my original parallel equivalent resistance formula because it's the easiest one for me to remember. So I'm just trying to be honest about the way I really do these problems. And 1 over Req is going to be 1 over 220 plus 1 over 100. My units are ohms in every one of those denominators. So the way I normally handle this is I will do 1 over 220 plus 1 over 100 in my calculator. And then I say 1 over that result, 1 over the previous answer, and I get my equivalent resistance. And to 3 sig figs on this, I get 68.8 ohms. And it checks out that that equivalent resistance is less than either one of the resistors in the original combination. Finally, I'm asked for the total current flowing through the circuit. So I equals V over R. Again, I'm thinking about the equivalent circuit now that just has one resistor. I equals V over R, equivalent, and that's 5 volts over 68.8 ohms. And since I used milliamps the first time around, I'll just do it again. I get 72.7 milliamps. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.